Yeah, thank you all for coming. It's my pleasure to introduce Alex, who will tell us further properties of Coulomb branches and examples.
Great, thanks for the introduction. So this talk is kind of designed to be a direct continuation of June Ho's talk. So let me give a quick outline, actually. I'll give a quick review of the construction, but it'll be very quick. And then after that, I want to discuss I'll give a little bit of a hint about your gauge case, where the representation is 0, and associativity. And I'll try to do in some detail. I won't be able to, to do all the details of this paper, we need many more hours, but I'll try to do the key details. And I'll try to do the abelian case in some detail. And then I'll discuss localization, which kind of lets us reduce some non-abelian cases to the abelian case. And then at the end, I'll give the BGL2 example as an application of that. Here's a quick review. Remember that the input of these things is a connected reductive group. Everything's over the complex numbers and the complex representation of the key objects that are used to define these convolution products are called R. When I write R, I always mean RGN. If there's something that isn't G and N, I will put it explicitly, which sits inside of a bigger thing called T. And so this is what we call triples of the G bundle over the disk. Trivialization over the open disk. So it lives over the affine Grassmannian of G, and S is a section of the associated bundle to N. And R is the subvariety where B sends S to a regular section. Maybe a quick recap of the notation. O is supposed to be the power series ring, and K is supposed to be the Laurent series ring. Always. Sorry, I'm moving blackboards quite quickly.
Oh, it's all right.
And so the main construction is this convolution product. On what's those the geo-equivariant Borel-Moore homology of R, whose definition June-Ho gave us at least last time. And the quantum version is the one where you put in a star action. And to have the visual, I'll draw the convolution diagram, which looks like this. GK cross R, that maps by a map called P to T cross R. Also maps to a map called Q. This listed product over GO. And then from here, there's an action map to R. It's supposed to take something over here and move it all the way back here. Okay, but it's supposed to be with R's. That's why they draw this figure diagram with a pullback. That's fine. Not too hard. Tilde, Q, tilde, and tilde is their notation, I think. And then for two elements in here, convolution product supposed to be, yeah. Pull back their tensor to there. And you observe that it descends down here. Okay. Push it down by M. And it's probably like one of the last things you know or the last time. What's up? This is the associated bundle to N. I don't know how to write that. It's E times GN, I guess.
And Alex, in the bottom right corner of the big picture, should it be
Yeah.
T? Yeah. Oh, actually maybe that was not the one I was asking. It
Is there?
It was
All right. The Zoom is very quiet.
Well, there are two people there and mine.
Did you guys hear or no?
Now it's
Oh.
better.
Yeah, sure.
Cool. Yeah.
Well,
I was just gonna ask about the bottom right corner of the big convolution diagram. Should it be R or T?
I thought it was R. No. Wait. Sorry. Yeah, you're right. Sorry. Thank you. It's T.
Thanks.
Okay, yeah. Sorry, let's get crammed. Put it in a box. This is an associative product with units that I guess they call E. And that's the fiber above the base point of the affine Grassmannian. Maybe it's worth pointing out that it's also linear over the base ring in C1, where the base ring is the equivariant cohomology of the point. And then for the one on the left, it's supposed to be commutative, so it's actually linear bilinear. And the one on the right is only linear in the left one. Okay. Hopefully I'll actually give a proof of commutativity later. I don't think we saw that. And then, yeah, sorry. This ring called A of G comma N. And then the quantum one is A H bar. In my talk, I'll basically only write this one and then sometimes say, oh, there's a quantum version, and either write the analog of the formula or not write the analog of the formula.
Remind that C star is loop notation.
Yes. Why is there another C star? It's because this is supposed to be like a loop group, and then we're incorporated loop. Thank you. Right. Talk a little bit about associativity. So notice that R G comma 0, this is just third. And sort of, I guess this business had already been done before in this case. There's a way to relate the case of arbitrary n to this one, which I'll describe now. So T for random n is a vector bundle. It's kind of pro-finite dimensional thing over this thing over G. And so zero section pulled back by the zero section is like this. This is like squares. You have to be careful about infinite dimensionality, but because everything was defined in terms of these finite dimensional pieces, this still works out. And in particular, we have map from AGN by restricting to AG0. So this lives inside of here. This is not an isomorphism now. And this is a map a priori in, let's say here. Modules over the cohomology of G.
Sorry, why, how do I know this is inclusion?
What, so, well, the fact that this is an inclusion is my next statement.
Okay.
Yeah. Lemma. That star is injected. So make it a quick proof. So there's, remember, R is filtered. This will come up again later also by these R less than or equal to lambdas, or lambda dominant coed, which is the pre-image of these closed pieces of Gur. So then the cohomology is also filtered. And because Z star is given by the zero section, that's a filtered map. So then it's enough to show Gur Z star is injective. Okay, but that from the description of these things that we saw before, you can just directly see that this coincides with the following map. Take that the lambda NO intersect NO. You take its equivariant cohomology, but it's equivariant with this finite piece where you mod out by Z lambda. And that includes into just the one of Z lambda NO. Right, and this is okay. This map is multiplication by the Euler class. and that's injective. So here's one way to prove associativity, which I got from the Webster seminar notes. It's kind of like a rearrangement of the way they did it in the paper anyway. So we can do this convolution business again with a different diagram. Well, this one. Put an R there and an R0 there, essentially. Doing the same kind of business, you get a map like this. I'm going to call funny A. So AGN corresponds to this R, and then there's an R0, so this will give you an AG0. And you end up in AG0. Way. So what you want to say is that this makes AG0 into an AGN module. If you had already proven that all of these are associative, then that's literally the statement. But one other thing you can do is prove that this product is associative and this action is associative, and that implies that this guy's associative by the injectivity statement. So I'll do like this. A of 1 star V2 equals a 1 and these are all the same proof. It's just the same diagram with slightly different things that you put in it. And I planned to draw the diagram, but it's actually a bit of a pain. Do I take a vote on whether we do it? I'm going to do it in words. So to prove, okay, we're supposed to do this convolution, but we were supposed to do it twice here. And then on the other hand, we're supposed to do a different convolution followed by this one. You splice the two diagrams together, and you get a big square where you can take some pullbacks to fill it in. And then, I mean, everything is going to commute on the level of maps. And then you just have to check that going both ways with the push and pull stuff commutes. And then those are going to follow from like properties of push forward and pull back based on the fact that some of these maps are smooth and some of these maps are, you know, nice in some other way, improper, I think.
You probably need Cartesian or something, right? It's like some kind of base change that you want to.
Yeah. So you fill in the diagram with pullbacks and then prove that the.
Got it. Yeah.
Yeah, sorry, I mean, saying this in words is not that helpful, but
Let
yeah.
us maybe, you know, if for some reason you finish earlier, then we can start going
Yeah.
this diagram.
Yeah, I think that's good. Same proof. Sensitivity of this AG0. I think one reason to do this is it's slightly easier to do each of these than AGN. I think that's one reason, but I mean, it's all basically the same. And then both of these imply AGN star in associative algebra.
Well, I guess AG0 is just known.
Yeah, I mean, one other thing you can say is this was done before,
Yeah.
right? Yeah.
Sequence there is that R or T, just because that's the T there.
This one's R. So like the diagram relevant here is the top one actually. Right. Yeah. Yeah. So that's the analog of the top row. Yeah, this is, I guess the fact that you don't have to pass to that top row is what makes this slightly easier. But in the end, it's the same proofs. Okay, let me not dwell on this too much more. Do the Boolean case. E equals T is a torus. Okay. This is the BFN notation. Y is the coate lattice. And given by n characters. C1 up to Cn. Right. So we're going to compute AC. Okay, how do we do this? Actually, you just kind of do it explicitly. So first thing to notice is T sort of up to nilpotence is the coate lattice. Maybe I should put like T reduced as well. Okay. And then on the other hand, so under this inclusion, what kind of I could use to define T anyway, maps into earlier times n. Okay. Okay, remember the little series ring. We have in this we get T is kind of the disjoint union over lambda of points times something. Yeah, everything up to reduced.
Actually, C and R.
Sorry.
Wait. You wrote something too complicated. This is C and R or
Oh, sorry, you're right. This is R, whatever. That's C. Okay. Yeah. And well, the next thing is that R is what I just wrote. Well, yeah, I mean, I guess because T is not literally implied, right? It's kind of like some in business going on, right? But if you take it reduced, then you literally get Y. So maybe I should have just written T reduced equals Y. Yeah, and then in the same thing, R is points times the like integral points of the thing on the right. Okay. And so sort of these are supposed to be our like fundamental classes. We write little r lambda for the fundamental class of one of these things. result is that these things would generate our algebra. So have that's the T equivariant homology of R is, I mean, I guess it's a module of this. Rack T is the Lie algebra of T times, I guess times R as modules over CT, I suppose. And then, so we're going to write a formula for the products. Don't think I can fit it here. Let D, what was the notation? DKL for two integers K and L. We're going to plug in values of characters in this function. So this is 0 if K and L have the same sign, and the minimum of the absolute values if not. Yeah, again, one of them can be 0, but then the numbers coincide anyway, so it's fine. Then in our abelian Coulomb branch, we have the following: R lambda R mu for two characters, co-characters, I guess. Lambda and mu is equal to, you take Ci are the characters defining the representation n. You raise them to the power of d of the values on lambda and mu. Make the product over the i's. There are n of them. And that's the coefficient of R lambda plus mu. That's the formula. Quick example. Simplest example is one-dimensional torus. And then n is a one-dimensional representation, which is the standard one. Then, I mean, I guess y is the integers. And then you have two relevant generators, R1 and R minus 1, which we call x and y. And then the math frac t, this is a, polynomial algebra in one variable that I call little t. I hope that's not too confusing. And then we get x, y equals, well, t, I guess. And I mean, you can take like powers of the standard representation and you get that power of t appearing here and stuff like this. This is just to like digest the formula in the simplest case. Okay.
What is the direct example?
Y, all the lambdas, I guess.
All lambda and y?
I think so. But this is like literally as modules because of the formula, you need fewer of them to generate, and in this case.
one square we have fields.
But you can't get to R minus 1 from R1, notably. Unless you invert a T or something. Okay. Right. So the way you do this is you remember the convolution diagrams. I guess say the way B intended this. And then they rewrite the operations appearing in the convolution as something kind of more understandable that you can actually compute. So identify this piece in terms of the decomposition that I told you before. This is like a union over pairs of co-characters of lambdas. This. Oh, this confused me when I was reading it. You should think of
The symbols of one.
what? Thank you. You should think of mu as lambda plus mu. This formula. Right. I mean, there's an explicit map you can write down. So well, is it P, Q, and M, I guess. Use this to replace P by something simpler. So P is a map from a product to a product. We're going to write it as a, there's a projection to T and to R. There's PT and then PR. And we define P prime, PT prime, PR prime as a map from there to there. This will be P prime by start with something here, which is a lambda nu and a S section. And then map it to something here, which is something in T and something in R, which like there needs to be a co-character in a section and a co-character in a section according to that decomposition. Well, we have one co-character, which is this one, and one section, which is this one, and then another co-character, which we want to be mu. So I'm going to write lambda minus, or nu minus lambda. And the section should be this one for reasons that mean that this works. Right.
Like Z lambda is a group element and he acts quantum it's action and
Yeah.
act back to
Translate it to where it's supposed to be. Yeah. So that's prime. The thing you want to say is that P is P prime. That's completely meaningless. But what you can say is that if you start in the middle and then you do something and then you go by Q here and then back by P prime, you will end up with the same as doing P. There's a second definition, which is, I wish I could try to fit it in here. A is a map, an endomorphism of TK times R. Actually, an automorphism. It's defined by I'll write it on the functors and points. So group element. This is a pair of a group element and something in R. That I want to map to, geez, the same over the same T fiber, but now the thing in R is a translate by lambda. Like this. This element is inside of TO. That helps press the formula.
So is lambda the orbit which you want? How is it?
Yes, exactly. Yeah. Sorry. I guess I just want to put like. But I mean, yeah. What Daniel just said is the definition of lambda. Thanks. Right. And now. We read, if you parse through the definitions, you get that the T component of P is the same thing as P prime TQ, and the R component of P is the same as P prime R Q A. Maybe I'm not going to write the formulas that I was going to write now, but I'll just say what they say, which is, so one thing we use abelianness for is that the things appearing in the convolution diagram are smooth. So when you look at Borel-Moore homology, which is like cohomology of the dualizing sheaf, right, you notice that the pullbacks by the maps of the dualizing sheaf are shifts of the constant sheaf. So that means that to compute the cohomology, you're computing cohomology up to a shift, right? Not some cohomology of a random sheaf, but like singular cohomology of the sheaf. And then the point is that by smoothness, back and we're gonna be C prime pull back omega. All right. Constant sheaf shift of okay. And then what's convenient is that you further replace P prime by P double prime, which on the individual components does, so I mean, why am I replacing P prime by something that's like these awkward factors floating around here? If you renormalize, you can just rewrite it as this. That's the product. And it literally is the diagonal. We'll just get that by renormalizing it. It does the same thing as P prime, essentially. And then in this, on these coordinates, in this picture, M is the projection to the cycloplecgy. And once the dust settles, end up with R lambda R mu equals M push forward P double prime pull back of the fundamental class. This thing. Yeah. Again, nu, so these are really different letters. Nu is lambda plus nu. And then you're left with computing this thing. We'll follow BFN and assuming that n equals to 1 to avoid wrist pain. Otherwise, it's all the same. So then there's only one character C, and then I'll write, I think I want A to be C of lambda and B to be C of mu. So the point is that we have to do some equivariant intersection theory of vector spaces now. That's what it's come down to. Picture. Follows. Don't remember. Look at this. So n equals 1 means the representation n is one-dimensional, so I'm putting NO is followed here. If you look at the formula above, this is the big vector space we're living in. There's a projection M in the second factor. Inside of there, there's O intersects Z8 plus B. Oh, which is supposed to be like, this is where we get the coefficient of R plus B from. And then on the other hand, the things we're multiplying correspond to these two vector spaces. O intersect Z8 O. Let's say it must be O. Oh. And then there's the other one, which is Z8 O intersect Z8 O. This one lives in here like that, and this one is diagonally inverted. And
so like we had 4 objects and we kind of threw one of them. So where what does the right picture correspond to on the
right. These are the two classes on the left side. Yeah. And we want to intersect them in the big thing. TK times R over TO is. And you project onto R. So I kind of got rid of this bit.
Yeah.
Yeah.
I understand. Okay.
Yeah. In the notation of BFN, this is called V12, this is called V23, this is called W. This is called V. I will call this I. Maybe they call it I. And then again. Sorry for this. Then tracing through the diagram, the point is R lambda R mu is X, where X is such that the M push forward of the intersection of these two cycles. Maybe I mean their fundamental classes is the I push forward of X. Yeah, you intersect them, you push them by M, and there exists a unique class X, which is obtained from V, which equals that thing, and that X is their function. Okay. Another point is because of the way this works, the coefficient in the formula is a product of Euler classes. And maybe I'll actually hide what the Euler classes exactly are because it's not that illuminating. I will end the proof here by saying, do Euler class computation. Blocks and quotation marks. The thing is that you trace through what this is, you're going to get some Euler classes, and they're going to depend on, well, I mean, they're Euler classes of these embeddings, give or take, and they're going to depend on like if these powers are positive or negative. So that's why that D thing appears in the exponent. There's going to be cases based on, you know, the signs of A and B. But there's sort of like fairly simple analysis of cases once you know what Euler classes can be. So this, yeah, writing it in terms of this intersection statement. Yeah, positive.
Sounds like something serious, but with this example, like it's t to the power of whatever restores the estimates, which is complete dimensions of whatever is left in this diagram. In some cases, where the quotient is zero, from zero dimension.
Yeah, thanks. There is a quantum version, which I don't know if I should write down. I'm just gonna, maybe I'll write down that there is a quantum version, and then it'll come up and until you believe me that this is what the formula is. So, maybe it's worth pointing out that the calculation actually shows that in the abelian case, the product is commutative. Because like we know exactly what the algebra is, and it just like comes out that it's commutative. So in the proof of commutativity, we actually use that, the abelian case. Put this as a remark. I have it written in the notes, which I'll send. So there's a quantum version. AH bar Cn. We have R lambda R mu is equal to a product from I1 to n again, but of something times R lambda plus mu. And this something is the classical one plus some H bars and some halves, which are coming from the loop rotation acting by weight a half. And maybe one other thing to point out is that well, CT no longer commutes with these. Instead, what you have, rel alpha in T dual, the commutator of R lambda with alpha is exactly H bar alpha lambda R lambda. So when H bar goes to zero, you recover the commutativity. Maybe I'll do the quantum version in the GM example, actually. And let's see. I have to remember the signs. So remember that I had X as R1, Y is R minus 1, and then T is a generator of T dual. And then here we have X, Y is actually, so it used to be T, it's now T plus H bar over 2. YX is T minus H bar over 2, so you can compute the commutative. Well, it's H bar. And then X and T commute to H bar X, Y and T. T minus H bar Y. Yeah. So you get a file algebra. Okay.
And if you take higher power of n, t stops being useless and becomes useful.
Exactly. Let's discuss localization. This is about how to use the abelian case to say something about the non-abelian case. So I'm not, well, okay. Start with a lemma, which is kind of like more conceptual, or like the significance is more conceptual than that I strictly need it to say anything else, but it is important. And if you do all the details, you do need all the, you do need it to say everything else. Okay, so there's this equivariant homology point. That's why I didn't put a thing right there, I guess, because it's a point. It says CH bar T. Let's bracket T file invariant. Embeds into AH bar for random G and N. So we're back to the general G case, by the way. And this is a commutative subalgebra. We kind of just check this. But the point is about this is that AH bar, this is a non-commutative deformation of A. Therefore, when you take the first order part of the product in AH bar, A gets a Poisson bracket. You know, by the usual thing, G equals like minus a half d by dh bar, A bar equals 0 or something of FG. So A, you know, the once we prove that A is commutative, spec of it, which is the Coulomb branch, becomes a Poisson variety. And this thing, because it's commutative subalgebra in here, it also maps in, or when you set H bar equal to 0, that's a subalgebra of A and it's Poisson commuting. CTW invariant inside of A, Gn, Poisson commuting subalgebra. Geometrically, spec AGN maps to a spec of that, which is this quotient. And all the horizontal functions are Poisson commuting. So, fact pi is a complete integral system. Essentially means that the fibers of pi are tori, and they're given by like the dual torus of the maximal torus of G. I think it was.
Non-singular.
The non-singular fibers. The important thing is to have this map pi for us, or for now. And I guess they call this thing the Cartan subalgebra. of the H bar. Okay, so our goal. Compare AGN and AT and T, where T is a maximal torus. Okay, I'm forever fixing one maximal torus. So here's a theorem about cohomology that Danielle told me we didn't state, so I'm going to state it because we're going to use it. You have a torus acting on a random, maybe I should assume smooth variety. And I write I for the inclusion of the torus fixed points. Then the pullback map, an equivariant cohomology of X, equivariant cohomology of the fixed points. Is an isomorphism after inverting characters which appear in the representation CDPX for all P in the fixed points. In particular, it's injective. So this is. I probably assume X is smooth actually.
I think you should also like stick define it.
Oh, well, T is that T, let's say.
Yeah.
Finite, or do you mean like a finite group?
No, like X, the number of fixed points. I mean, I'm not sure it worked exactly like that. If XT is, has some attribute. So,
yeah. Okay. So you have to yeah. I mean, it's a bit sloppy, but I guess you're right that if I say this, I need to assume there's finitely many of them.
Yeah.
Otherwise, I have to invert like the Euler classes of the normals to the fixed point locus.
I'm just not sure it works exactly like first you get zero, like if you have a point, it's zero.
Yeah.
I'm just not sure it works like that.
Oh, I mean, I think I have to say non-zero characters,
Yeah,
but in any case, but yeah, sorry for not having that.
And I mean, I guess to say that it's exactly, you should also like you use, if you say injectivity, you use formal equivalence. That if you do localization, then schemes suddenly don't become zero.
Yeah. Yeah. Thanks. So, okay. I'm going to take this as a black box. And we're going to proceed with the goal. So we first note that the Weil group, which is NT mod T as always, acts on the cohomology, the T equivariant cohomology of R. Or more homology, sorry. So R is RGN and T is T. Maybe I'll even to be completely precise and put RGN. Well, this is because the normalizer acts on the geometric thing. And on the T equivariant things, T fixes them to the algebra. Next. If I start with the G equivariant then, which is where, well, AGN. And then that's a modular over H the other side point. So I can tensor up to the cobalt of the torus. That emits a natural maps with the equivariant homology of R with respect to the torus. This is a nice word. Maybe that's 0.1, and 0.2 is that without tensoring, this is literally, you take this thing, on it acts the Weil group and the invariant, sorry. I'm going to skip the proof of the it's kind of like usual cohomology thing. So now, in R, which is RGN, there lives an RTNT, the inclusion iota. Proposition. There exists a dense open subset TO of T. T mod W is the base of this thingy, this map from the Coulomb branch down. So I take this dense open and then I look at the corresponding open upstairs, and over that, the push forward map by iota from T equivariant homology of R TNT, which is a TNT, to T equivariant homology of R is isomorphic.
Is this inclusion just comes from inclusion of Grassmannians, which is enlarging the structure?
Yeah. So group sketch. Let's I call it GRGT. This variable only exists within this function in the program, so you can forget it after I finish the proof. So there's two types of weights, I guess. There's the non-zero weights in N, and then there's the weights of the ideal representation in K of roots. I want to combine them into one thing. And notice that each of them defines a hyperplane inside of T. So for alpha in GRGT, alpha bracket equals 0 as a hyperplane. And T0 is the complement of all of those hyperplanes. They call this generalized roots. So then checks that first of all, alpha in T0 is precisely the same as saying that if I take RGN and I take the alpha fixed point, so I take the one parameter subgroup generated by alpha, I take the fixed points with respect to that, that's the same as the fixed points with respect to the whole torus. And then the other thing you can check is that over T0, the fixed points, these fixed points are the same as actually the fixed points for the torus one. Take R for the abelian thing, and then you take torus fixed points. Those are the same as the torus fixed points for GN, as long as you're living over T0. And then this is the point where we use the localization theorem. Kind of why I was sketchy with the statement of the theorem, because I'm kind of sketchy with how I use it anyway. You cannot forget those letters.
So, like the end of the proof is the goal function, like you have.
Yeah, there's like two localizations that you apply.
Isomorphic to the equivalent homology of this.
Exactly. Yes. Yeah. Yeah. I guess there's a T localization for the abelian one and a T localization for this, but they're the same. So.
And over T0 means that you also localize before.
Yeah. So when you take the cohomology, the coefficients kind of have these inverted.
Yeah. Okay.
Mark. In particular, iota star is injected. Yeah. Embedding. Well, we were looking at the map. Where's it? There. From the abelian one to the non-abelian one. Okay, but on here, I told you there's a while group action, so I can take the fixed points. This includes in here. Listen. And this is an embedding of, okay. HG points modules. But, okay, well, both sides are algebras. Theorem. This is an algebra map. Also sketch. So. You draw the same kind of convolution diagrams a couple more times, which I'm not going to do. To the ones for the product. Give And you conclude that the abelian Coulomb branch, non-abelian Coulomb branch, both act on something, which is these torus equivariant for a homology of R. And this is a bimodule, like the actions could be bimodule. And then you do the same proofs again. The bimodule structure is convenient partly because, so I'm going to write the actions as star because it's defined by same convolutions. So first of all, there's the like left action. If I take something on the left, I send it to C star the identity. The identity is always the same element. You take fiber for the base point in the Grassmannian. So I end up in AGN. And this is the same as the map iota before. And there's the other one, right action of this. This turns out to be the same as restricting the G action to T action. Okay. And so the left module structure, so the abelian one acting on that is W equivariant. This is because when you draw the convolution diagram, it's going to be equivariant with respect to the normalizer of the torus. It's not a mystery.
So is rest G0 T0 like inclusion of W invariance?
Yeah. On the level of homology. Right. So I want to prove that that's an algebra map. I'm going to use this. What's an algebra map? Let C1, C2 be in the left-hand side, so I'm going to take this thing, but I want W invariant. Right? Then by the first property, iota star CI for I equals 1 and 2 is the same as acting like this. But also this is W invariant by this property. Therefore, by 2, there exists CI prime such that this invariant element is equal to 1. Okay, and well, the point is that the map upstairs, iota star, just sends C to C prime. Okay, but then we conclude by associativity of the actions. So it turns out it's again another instance of the same proof, but I didn't draw.
Anti-algebra map, but maybe most question is reversed, so it will automatically.
Yeah, exactly. Actually, let me prove commutativity now.
Oh, there is no continuity for this activity.
Yeah, but let me prove commutativity of everything now. The bit where you can AGN. Commutative. So from our computation, we know AT is and in particular, I guess. It's just, I take the thing which is ATN, and then I pass to, you know, the open T0 that remains in algebra because, you know, localizing. Then we have projections like this. G equivariant of R, which is supposed to be a GN, includes as the doubly fixed point into T equivariant homology of R, includes into this. This is a isomorphic to I guess I already wrote this. I guess what I want to say is this. The same proof as the previous theorem. Well, probably actually just the theorem, but in any case, shows. This is an algebra map. That's okay, but so the thing which we want to prove is commutative includes into a commutative algebra.
So times fine.
Yeah, so let's see. I want to do the PGL2 example. To do that, I need to do a little bit more. So in the little bit more, maybe I'll just give the statement. We will not do the PGL2 example, and then hopefully I'll finish not late. First, recall from near the beginning, I remind you that R just filtered by is R. Let's think of lambdas. Yeah, or lambda elements go away if we stay right as lambdas. You get AGN is also filtered. And the associated gradient is created by Y plus. Maybe fact. GR A as a module over the equivariant homology point. Is like this. This is no. And each of the pieces looks like the equivariant homology point is as a module. Let me give you the result that lets you compute, and that I'll use to compute the rank 1 example. But in principle, you should be able to use it to compute a lot of examples in terms of the abelian case. Run. So I wrote it as 2 parts. Part 1, I have 2 things in my class, and then I have coefficients like this. So this means it's invariant by the stabilizer of lambda and W, and then this one invariant stabilizer mu. Then, so in the graded algebra, like in the graded algebra, it's just very accepting these fundamental classes. And you try to multiply them together. And indeed, the formula is and that we've seen in the abelian formula times FG the sum. Sorry.
Do we here want to write W lambda instead?
Oh, I think I did. What happened to? Yeah, sorry. Okay, so that's on the graded, but something you can say on the upstairs without taking graded is if you have lambdas corresponding to closed orbits in the Grassmannian, then you can give a formula for these things. So in fact, the formula I'm going to write always holds on the associated graded, and then for the closed ones, it even holds upstairs. Let's see. So lambda such that G lambda is closed. G orbits. Then I can put any coefficient there. So up to taking the inverse of this isomorphism, this element is expressed by a sum over the Weyl orbit of lambda. Weyl acting on this thing times. So remember, this is the generators in the abelian case. And then you have to normalize by an Euler class. The Euler class of this tangent to the piece of the Grassmannian. So this is right. This comes from the local. If you study the equivariant localization theorem, you realize that there's going to be a formula that involves dividing by these Euler classes. So that's where that comes from.
What is G lambda prime? Is it a T? Is it a T right now? The lambda prime is not necessarily dominant.
Oh. second. Yeah, that doesn't mean anything. Oh, I think I just mean tangent to this point of Ger lambda. Yeah.
And like the point is like z to the 1.
Yeah.
Oh.
Sorry, thanks. So let's squeeze in another theorem. Yeah, I would have said more if there's time, but I'm just going to give this as the statement. The Coulomb branch algebra and the non-commutative one are both finitely generated. Actually, I mean, well, okay. And you can say by dt together with a finite set of R lambdas for lambda in a finite generating set of put file chamber in quotes because you have to account for the fact that there's generalized roots going on and might split up into a smaller cone. But in any case, you intersected with the y plus, and that's a finally generated semi-group. And you just take a set of generators, and that will generate the homology. Yeah, sorry that I don't have time to say much about that. So I'm just going to use that board to do something with PGL2 now. And let's do the simple PGL2 case where the representation is 0. So I'm working with the Grassmannian, but actually, okay, the general n case is not that much harder. So you observe that your G has 2 closed orbits. The trivial one, which is like your superscript 0, and also your lambda 0, where lambda 0 is it's a generator of the positive coeids. In this case, well, the coeids are Z. Yeah, I can just take that to be positive coeids like this. And here you get a P1 for the closed orbit. And then also remember that C, T, W, so T, so this is a polynomial algebra, and then W is the group of 2 elements, which acts by negating the generator, so it's a C squared. And the point is that this set, I can just take lambda 0. There's just one of them is enough. So, right. All right, delta for T squared, eta for the fundamental class of the one thing that will be enough. And I mean, there's also one more element we need, which is T times it. Because in here we only have T squared. And these generate A. And then using the theorem, the top theorem, you can just compute that like I star inverse of eta is R lambda minus R minus lambda over T. And then C gives you a plus, I think, and no T, because there's already a T. And from here, you can just get, like, you can spot a relation that exists, which is, so up to, I'm going to drop the iota star. and I'm gonna forget what the relation was. If I take, yeah, so if I square them, I get basically the same element, right? C squared minus T iota squared, I think.
T squared.
Yeah, why? Because I'm gonna do square this, I'm gonna square this, I get a T squared, and I need to use one of the generators. Thank you, it's a delta, which is a T squared. I believe I get 4. And I mean, you can just conclude that A BGL2 is 0 is literally isomorphic to C delta iota C mod this one relation. C squared minus delta iota squared equals 4. If the representation was non-zero, but I took you know, some n-dimensional representation, then I get 4 times delta to the n or something here. I'm not going to bother with that. And then you can do the quantum version. You get some h bars. The commutators are no longer 0, and then you might get some h bars in this relation. Well, I think you get 2 correction, h bar corrections to this 4. Using, yeah, I mean, the same theorem kind of holds with the quantum coefficients from the other ones. You can, it's fun to just compute that. So maybe I'll finish with saying one general thing. Sorry, I'm having to move boards for this last thing. There's this, the geometric picture I think one's supposed to keep in mind is that there's this Coulomb branch, I guess they call it MCGN. This is an integrable system over C over W. And by the stuff we did where you pass to T0 and the algebra is isomorphic to the abelian one with W invariant or whatever, you can conclude that this is birational to cotangent bundle of the dual to the maximal torus mod of algebra. Right, but this is sort of the birational isomorphism happens over T0. And in particular, so what happened here, this thing is 2-dimensional. Yeah, this thing is 2-dimensional. The rank of PGL2 is 1. And in general, you can see that like because of this, you can conclude that dim of MC is equal to twice the rank of the group. So in that case, 2 in general this. Right. I mean, they proved geometric properties about this that I didn't have a chance to get to, like it's normal and stuff. Yeah. Which probably good stuff. But okay, I'm just gonna end there.
Zoom? Any Zoom questions?
That was great. Thanks, Alex.
Yeah. For this, you can think that it's a variety with a Poisson structure and a map down to something affine where the fibers are tori of half the dimension. So what turns out to be true is like this thing is symplectic, and over the regular locus of this, the Poisson structure can coincide with this one. So it is symplectic.
Okay.